This is a worm gear drive from a movable screen from a classroom. The input to the drive would be a motor over here that would turn a smaller pulley that would be belt driven to this larger pulley. It would be a tooth belt. So this is our input. As you can see, I've marked this gear so we can watch the number of rotations as we turn this around once, twice, 14, 15 times. The output shaft makes a complete revolution. So we have a 15-to-1 gear reduction. You'll also note from this view that the input shaft is perpendicular to the output shaft and they do not intersect. Very large gear reductions in a fairly small space are possible with worm drives. Another thing to note is that a worm drive is not easily back driven. So if I try to apply torque to the output shaft, I cannot turn the input shaft. This might be a desirable feature for the application. In this case, we wouldn't want the classroom screen to be able to lower itself due to its weight. Looking inside the device, we can see how it operates. This is the input worm gear, and this is the output helical gear. So as the input turns fairly quickly, you can see the output turn fairly slowly. The gear reduction is related to the number of threads on the worm and the number of teeth on the output gear. We can see with this worm we have 2 threads. One starts here, and after a half rotation we can see the other thread starting. So there are 2 threads on this worm. This gear happens to have 30 teeth on it, and that's what provides the 15-to-1 gear reduction. You'll note that with a worm drive we have a significant amount of sliding contact between the teeth. Hence there's lots of friction losses, and these gear drives are very inefficient compared to other types of gear drives.